All right, welcome everyone. This is lecture 4, which I've pre-recorded today, because I won't be able to teach on Monday, the 28th. And so I hope this will do for all of you. We're going to do a topic that's, I think, a little bit difficult. So, but I hope I'll be able to explain it to you in detail and not to confuse you too much. So we're going to work on paragraphs 15.5 and 15.6 on surface integrals. And the situation we have is first of all that we have what is called parametric surfaces. I'm going to do this in R3. And so that's a map, let's say R, which I'm going to be taken from a square in R2, spanned by AB, the interval, and CD, the other interval, and I map this interval to some surface. And so U, V is mapped to R of U, V, which is a vector. And by doing this for all U and V in this square, I parameterize a surface. And this, since every vector has 3 components in R3, R of U and V has 3 component parts, X of U and V, Y of U and V times J, plus Z of U and V times K. And so this can be done for rectangular domains in R2, and but we can also do it for other domains. So in general, I have a map R from some domain to R3, where D is some domain in R2. And very often, actually, this R of U and V actually has the form U times I plus V times J plus F of U and V times K. And in that case, I can really see that I have in my UV plane, or the XY plane, if you will, I have this domain D, and above it, I have some graph of that is my surface in the Z direction. And so this allows me to make different surfaces, and in fact we can make lots of surfaces. So things could really look like this sort of graph of a function, but I can also have things like that, which is a donut, and I'm going to give it a bit of volume like that. And so this is a surface in R2, a donut, so to speak, which has no boundary. You could walk along it as you could walk on a sphere, and on the edge of a sphere, like we do on Earth. And in this case, you would never fall off, right? So this is a surface without a boundary, a donut or torus. So what we'll have later is that we have a function f of x, y, and z, which kind of lives on this surface, just as we had functions f and x and y on a line or a curve C in R2 or R3, in this case in R2, because f depends only on 2 variables. And so just as we wanted to integrate f over this curve, now we would like to integrate f over a surface. And we're going to denote this in this way. And this is the notation for the surface integral. This is the surface integral of f over the surface S. And what we'll do today mostly is to worry about, well, how to make this thing computable. Just as before in the line or in these line integral cases where we had this dr line element, here we have this surface element ds. And that is the thing that we have to think about most. What is this element? And if we can write that element in terms of u's and v's, or in this case, well, right, indeed, u and v, then we can rewrite this entire integral in terms of a normal double integral over u and v, which we are able to solve using the methods from your Calculus 2 course. And as you know, these double integrals essentially are just double single integrals. And so in the end, we just have lots of single integrals. So if we take a point, let's say R naught, which is R of U naught V naught. This is a point in 3 space. Then we can, and this is a point on the surface. Let me put that a little bit to the side. Then through it, I can vary U and V in the surface, and this gives me these curved lines. Yeah, so this line here could be R, where I keep U fixed at U naught, but I vary V. And this other line is the line where I keep U V naught fixed, but I vary U. And so if I trace out a small part of that, then I get a small bit of element, an area like that. And this is my ds. So how do I measure its area? Well, then I, from this point that I start at, I look at the tangent vectors over here. And these tangent vectors are dr, du times du, which is, so dr du itself is a tangent vector, but I'm only taking a small step of length du, and dr dv times the infinitesimal element dv. Yeah, and that gives me vectors that have the same, that have, oops, that's too big. That gives me these tangent vectors. And now I'm going to draw this rectangle here to match the length of these vectors. That's why I shortened it a little bit. And so the question is, what is the size of this parallelogram? So if I do this sort of flat, right, it doesn't have to be a rectangle, then the area is given as the area of this rectangle. So that's the area ds. So you've learned in linear algebra, I hope, that the area of the parallelogram spanned by dr du, which is one length, one vector, and dr dv is this cross product times du dv. So in general, if u and v are two vectors, then and they span a parallelogram, then the cross product of these two vectors gives the area of the parallelogram, and or the length of that vector, to be more precise. And so du and these differentials du and dv are seen here as scalar factors, and so they can be taken out of this length. And this we also encountered as the normal vector. So in this in this picture, I also have a normal vector. Let me redraw that over here. Here is my normal vector, which I also compute with the same cross product. So in a way, what I've written here is the length of n, the normal vector, times du dv. All right. So what is that? So this cross product, the dr du cross dr dv equals this determinant. With all these partial different derivatives of the component functions of R with respect to u and v, and then putting them in this kind of matrix with I, j, and k on top. And so this is often written as, so I can write it as I times this subdeterminant, which I'm going to write as dy z dx, sorry, uv minus j times dxz duv plus k times dxy duv, where one of these things, dyz, for instance, duv equals dy du dz dv minus dz du dy dv. So one of these subdeterminants, etc. So that's quite a mouthful, obviously. And so then the length of this cross product is the sum of squares and then taking the square root. And you just hope that this term, which has to enter in your integral, doesn't mess up the idea of integration, right? Because of course these are very big terms often. So in the simplest case, going back to my original surface integral, so what I've talked about here is just this element ds. So we are kind of summing elements of ds, which are areas, so small infinitesimal areas of my surface, by parameterizing this surface with a parameterization r. And then if I want to do an integral with some funny s, what I'm actually doing is essentially looking at the height above this surface element, which has height f, and then summing them over all these surface elements as if you would make one of these Riemann sum things and then taking limits. So in the simplest case, this height is just 1, and then what I have is really just the area of the surface. So the area of the parametric surface is this double integral over S of just the element ds, just as the line integral over a curve of dr gives you the length of that curve. And now the surface integral, the more general one, the surface integral, of f of x and y and z over S parameterized by this parameterization with component functions, which we denote by this notation. That's the thing on the right. So how do we compute it? Well, first of all, the first way of writing that is to say, well, I evaluate f at all the points r of u and v, where u and v now go through the domain of my parameterization. And then I look at the size of this element ds, which we've seen can be computed by taking these areas of these parallelograms and du dv. Yeah, so rather than where here x, y, and z has to be an element of S, I'm parameterizing this surface where x and y and z are now functions of u and v everywhere. And so my new integral becomes an integral over u and v, where u and v go over my domain D. But of course, rather than looking at x, y, and z here, I now have to look at r of u and v, which of course is a vector with components x, y, and z. So to spell that out, and this barely fits on a line, I have to fill out my component functions in F and then compute the length of the size of this area element, which, as we saw, is given by I'm trying to put them in the right order. Of course, the order doesn't matter. du dv. So this very last integral is a standard double integral, hopefully computable for a certain domain D. And sometimes you'll have to rewrite that thing in terms of polar coordinates or in cylindrical coordinates if the surface happens to be something to do with a cylinder, or spherical coordinates if your surface has to do with a sphere. And so then you have to remember those transformations from Calculus 2. And I will be reviewing a few of those without explaining them in detail because they were already done over there. Yeah, so D is the domain of R. All right, so let's make this a bit more concrete and do an example. We would like to compute this surface integral of z ds over a conical surface. So a conical surface is a surface that looks like a cone, and I can draw it like that. And then I have my other planes like that. And here my height is 1. And the conical surface is given by z equals x, the square root of x squared plus y squared and z lies between 0 and 1. So for every z that I choose between 0 and 1, square root of x squared plus y squared equals a number is a circle. So for instance, this circle. And so if I now change z, I trace out this cone. Okay, and I'm actually looking at the surface of this, right? It's not a volume. Maybe I should do this in a color. I'm not that sure that helps, but we're doing this over this surface as a 2D object and not as a filled object. So note that z squared is equal to x squared plus y squared on S by simply squaring the equation that I have. And so that allows me to parameterize it with r of x and y equals x times I plus y times j plus the square root of x squared plus y squared times k. But since I've just introduced the notation with x and y being component functions of u and v, I'm going to change my exposition from the book and say, well, I actually am going to write it in this form. So that this x of u and v is u, and y of u and v is v, and z of u and v is the square root of u squared plus v squared. Right. So if you understand what you're doing, I'm more than happy if you actually forget about u and v and just work with the parameterization in x and y. But just for this first example, I thought it would be better to not confuse you and to do everything in u and v, and then to have these kind of trivial component functions for x and y being the first component and the second component, like this. So in this u and v notation, to get closest to the formulas that we had at the beginning, we noticed that we had to compute this area element. And to do that, we have to compute all the partial derivatives of the component functions with respect to the variables. So I'm just going to write them down. dx du, well, that's clearly 1. And dy du is clearly 0. And dz du, then I have to take the derivative of this function with respect to u. And so that gives me 1/2 u squared plus v squared to the power minus 1/2 times 2u, which is u over the square root of u squared plus v squared, which is u over z. And if you thought, well, that's obvious, because I already knew that z squared is x squared plus y squared, or in this case, u squared plus v squared. And so if I take the partial derivative with respect to thinking z as a function of x, or in this case of u and v, I can say 2z dz du equals 2u, from which I follows that dz du is 2u over 2z, which is u over z. Yep. All this is just one of the same computation. And again, the book presents it in this last fashion, but I think it is better to do it first, making everything completely explicit in terms of this u and v, and having these kind of trivial components, x of u and v being u and u of y of u and v being v, because this always works. All right, so these were the partial derivatives of x, y, and z with respect to u. And then we're going to do the same with respect to v. The first ones are 0 and 1. And out of symmetry, I hope you agree that dz dv must be v over z. So with these partial derivatives, we can compute dy, z, du, v, which means that I take this one times that one minus this one times that one, right? I wrote them in this kind of 2x3 matrix, not for nothing, so that I can see these subdeterminants straight away. So this is 0 times v over z minus u over z times 1. So this is minus u over z. And in a similar fashion, the x, z, the u, v equals v over z times 1 minus 0 times u over z, which is v over z. And the last one, which I'll write on the next slide because I'm done on this slide, but I can show you before getting there, is that I have to take this subdeterminant, which is 1 times 1 minus 0 times 0. And so that's 1. So I've done all my partial derivatives. I've done all my subdeterminants. And so I can compute this element ds. And it equals the first of these squared plus the second of these squared plus the third squared du dv. All right. So this is also equal to u squared plus v squared plus z squared over z squared du dv, which is equal, since z squared is u squared plus v squared, it's also 2z squared over z squared, which is just square root 2. So after all this work, it seems that the only thing we pick up is a factor square root 2, which is not really surprising given the fact that this image is, well, the square root 2 obviously comes from the fact that I've tilted this cone in an angle of 45 degrees. And that changes the area in the xy plane by a factor of square root 2 if you change it to the surface S, if you map that to the surface S. Okay. So now we've done all the, or I should write du dv here and also there. So now we've done all the preliminary work and we can actually do our computation. So now this integral that we want to compute of z ds equals, we have to write everything in terms of u and v. So we have a double integral over the domain, which we're going to talk about in a second. Z was equal to square root of u squared v squared du dv, and the square root 2 comes in front. Yeah, so this one together with that one is the ds, but I'm taking the square root 2 out in front. So the only thing I haven't written down is what my domain is. And let's go back to this picture for a moment. So if the height here is 1, then clearly the UV domain that is underneath here is equal to a circle of radius 1. Yeah, because precisely then, if I'm on a circle of radius 1, then the square root of that is 1, and so z is 1. That's the largest value of u and v. And so I'm doing this over a domain 0 less or equal to u squared plus v squared less or equal to 1. So since this is a circular domain, it makes sense to not write it in this form, but to write this in polar coordinates. Where the square root of u squared plus v squared is nothing but r, which should not be confused with the parametrization r that we had before, where this is the r from r and theta. And so in that case, you remember that the surface element in polar coordinates becomes r dr d theta, right? And this element here you pick up from doing the transformation to polar coordinates. So this integral, let me put a little star behind here so that you can see that I'm continuing that computation, is the square root of 2. I do a full circle, so 0 to 2 pi. The r value goes from 0 to 1, r. That is the square root of u squared times v squared times the element for, which I put in brackets to just make that notationally clear, r dr d theta. So this is square root 2. The integrand does not depend on theta, so we just pick up a factor of 2 pi times 0, 1 r squared dr, which is 2 square root 2 times pi. And then you get 1/3 r cubed between 0 and 1, so that gives you 1/3. And there's your final answer. So in this case, actually, we saw, let me put a little line there, that the surface could be projected onto the domain in the x, y plane. So I had this picture where I had a surface like that, and I actually made the projection onto this domain. And I did introduce the u and v just to get close to the original notation, but I really didn't have to do that. I got just stuck with x and y in this case. And so let's do that right now. So then, if I have one of these domains, so here I have a surface which is given by g of x and y and z is 0. And I have a little area element in it, but I also have a projection of that onto my domain D. So if this thing has size dx dy, then it depends on the angle of g, how much ds is changing. So let's say that locally I have this normal vector, which is not vertical. If it were exactly vertical, then of course the ds element on the surface would be equal to dx dy. But if it's really tilted, so if I have a surface which is really slanted like that, then this element becomes much smaller than the projected element over there. So if this normal becomes more tilted, and if it becomes even further tilted, then no, it's the other way around. So then this becomes small, while this remains the same. So in other words, what I have to do is to see how this normal vector, how it decomposes into a vertical direction and the orthogonal complement. And to make a long story short, this ds element can then be computed as this ratio. So this inner product n with k being the unit vector in the z direction, measures exactly the compression of this ds element, or actually of the dx dy element in the projection. Yeah, so if we write that, so we know that this normal vector actually is also equal to the gradient of g. And so, in fact, what is written here is that if I have one of these functions g, then if I look at its gradient, that gives me the length of this normal vector, and the projection of n onto the third component is given by the third component of g, of gradient of g, which is g dg dz. So here's a direct, different and shorter formula for this, the computation of ds, which does not involve all these component functions x, u, x, y, and z of u and v. So in that case, our surface integral becomes the domain on which I have projected my yes. The domain on which I have projected my surface times the gradient of g, x, y, z, dg, dz, dx, dy. So, I invite you to reinterpret what we just did in terms of this fashion. I'm going to do another example in a minute, but the example that we just did with this conical surface is actually also an example of this. Right, so this makes computation of the ds element easier. So let's do an example. You can pause the video if you want to digest that. So the example I'm giving is where the surface is given by the following function x, y, z. Is x squared plus y squared minus z squared plus 1 equals 0. And z lies in between 1 and square root 5. I'm not going to draw this. So notice that z squared on this surface is 1 plus x squared plus y squared. And this is always greater than or equal to 1, because x squared and y squared are positive. And so this, for one, it tells me that z equals 1 plus x squared plus y squared. And this is the g of x and y that appeared on the previous slide. So that's this one over here. And furthermore, if z lies between 1 and square root 5, then x squared and y squared go from 0 up to 4. So that z squared is then maximally 5 and z is maximally square root 5. And this is a circle of radius 2. That's not a very nice circle. And I can project my surface, however it looks, onto this domain in the xy plane. So we're given, you can see how we can go back and forth from this description, or even this description. If you're given this, then you can find capital G by first squaring it and then saying, well, if this is always equal to that, then this must hold. And now we have written this a capital G equals 0, and that's what we want. So the ingredients that we need are the gradient of G, so the partial derivatives of G with respect to x, y, and z. Well, that's 2x times I, 2y times j, and minus 2z times k. These are the partial derivatives of this expression with respect to x, y, and z, respectively. And the last of these components is dg dz. And so that's minus 2z. That's all there is to it. So ds equals the length of 1 over 2z. We don't care about the minus because we're taking absolute values in a minute anyway. We're squaring and taking square roots of the vector. I'm now writing it in vector notation because it's slightly more transparent, I think. Yeah, this is my normal vector scaled with dg dz to account for the kind of compression factor. So this is just a vector and we have to look at its length. So this is the square root of 2x over 2z squared plus 2y over 2z squared. And then a plus minus 2z over 2z squared. And so that's x squared plus y squared over z squared plus 1. So that is actually 1 over z, 1 plus x squared plus y squared. And I'm forgetting the dx dy's everywhere. Wait a minute. No, I have to be careful. I'm writing it like that. No, this is okay. But now this 1, let me first read it like that. Sorry, guys. So this is x squared plus y squared plus z squared. And what is z squared? Well, z squared now has to be found on the surface. And so z squared is equal to, it's equal to 1 plus x squared plus y squared. And so this is 1 over z times 1 plus 2 x squared plus y squared dx dy. So if we now look at the entire integrand, z ds, it is given by 1 plus 2 x squared plus y squared dx dy. And that is what we need to integrate. So finally, our surface integral is given by this integration over x and y, where my domain is 0 x squared plus y squared less than 4, less or equal to 4. So that's my circle of radius 2 in the xy plane. And now we should be back to familiar ground, because this is again a circular domain. So we switch to polar coordinates. And so this is 0 to pi, 0 to 2 in this case, because the circle is radius 2, 1 plus 2r squared. And the dx dy again becomes the element in polar coordinates, which is r dr d theta. And this integrand again does not depend on theta, so I pick up a factor 2 pi. And that's one thing. And the other thing is that I have to integrate this thing, but here there's an r squared, and here there's essentially the derivative of that. So I'm doing a substitution, u equals r squared, so that du equals 2r dr. And so r dr is 1/2 du. And if r goes between 0 and 2, then u goes between 0 and 4. Square root 1 plus 2u times 1/2 du. All right, so from here on, it's a standard integral. And so this is 2 pi, the 2 pi cancels with 1/2, so that's just pi, times 2/3, 1 plus 2u to the power 3 over 2, times 1/2 to counter the chain rule. That's this factor 2 between 0 and 4. And so if you work that out, that's 27 minus 1 pi over 3, which is 26 pi over 3. All right, so just to summarize before I close, we've covered the surface integral, parameterizing the surface over with some function r of u and v. And if you're unlucky, then you really have to work with that. And then you have to work out these cross products and find out what the element ds is in terms of that. And so that's this formula. Then you get a problem for u and v, and you either have to do that straight away, or you have to go to other coordinates such as polar coordinates or spherical coordinates, as we will see in a minute, and work it out. In the special case that the surface can be projected onto the xy plane, then you can do everything in terms of x, y, and a function z of x and y And that allows you to compute this area element much quicker, as I just showed you. Yeah, so that's our one.